Hello, this paper presents an effective model for human cognitive performance within a human-robot collaboration framework. The authors of this paper are Mohammad Khurram Monir Rabi, Mubashar Altaf Khan, Ali Karamadani, and Stephen Jong from North Carolina A&T State University, USA. Here is the outline of this presentation. First, we will talk about the motivation behind this work, followed by the brief research problem for the mathematical modeling of human cognitive performance. Later we shall talk about the technical challenges and then discuss some of the existing approaches that several other researchers have been trying to solve this problem. Next, we will highlight the main objective of this paper and then discuss the proposed model for human cognitive performance. Finally, we will present the simulation results of the proposed model and then wrap up the presentation with the conclusions and some insights into the future work. This research is motivated by the rapid developments in robotic technologies, which have laid the grounds for the use of robots to develop a variety of applications based on human-robot interactions. These applications range from manufacturing, packaging, healthcare, warehouse management, and cybersecurity, to their economic impacts on future developments and intellectual and cognitive skills. It is not far that humans and robots will collaborate at the workspace to achieve common goals to improve the efficiency in handling the shared tasks in a human-friendly and secure work environment. The integration of human decision-making into a human-robot collaboration framework minimizes the chances of deviations in job handling from the expected and desired behaviors through conceptual coordination against the involved uncertainties. Before discussing the technical challenges of this paper, let's briefly review our research problem. In a human-robot collaboration setting, human cognitive performance can be impacted by human cognitive workload, robot performance, and human physical performance. Then, the research problem is to develop a mathematical model to describe the relationship between human cognitive performance and the contributing factors, including human cognitive workload, robot performance, and human physical performance. Further, we are interested in understanding the relationship between human cognitive performance, task complexity, and the robot's performance. So what are the challenges of mathematically quantifying the human cognitive performance over time in a human-robot collaboration setting? Various challenges exist that are very much difficult to quantify. Some of the notable challenges are the human cognitive workload and/or the human physical workload, the shared task complexity, and the performance of the robot. Due to those challenges, mathematically model the human cognitive performance in a human-robot collaboration setting is a big issue. In the literature, several techniques have modeled human physical performance in human-robot collaboration settings. However, a more comprehensive model is needed to describe a human operator's performance in terms of both physical and cognitive performance in a human-robot collaboration framework. In an attempt to address this problem, the researchers have proposed a linear relationship between human cognitive performance and robot performance. These results do not describe the mathematical relationship between the human cognitive workload and the contributing factors such as task complexity and human utilization. Recognizing the limitations of the existing research, we propose a novel, effective, time-driven mathematical model for human cognitive performance within a human-robot collaboration framework. Human cognitive performance indicates a human's cognitive capability to perform mental work. The proposed model considers human cognitive performance as a function of human cognitive workload, robot added workload, and human physical workload. Here, we refer to robot added workload as the workload added to the human operator due to the robot's mistakes. The proposed model considers the cognitive workload as the dominant factor in quantifying human cognitive performance. Further, the developed model takes into account the effect of human physical and robot performances on human cognitive performance. Here, we describe the human-robot collaboration setting that we have used throughout our discussion. Consider a human-robot collaboration scenario, which is symbolically shown on the right side of this slide, in which a human and a robot are collaborating to perform a shared task. In this human-robot collaboration setting, the robot can be utilized to perform repeated routine work, while human intelligence can handle more complex tasks such as decision-making. The robot performs the task based on instructions received from the human in the form of cognitive signals. The more the robot can perform a task successfully, the less human supervision is required. If the robot commits a mistake in picking or placing the objects from or in wrong conveyors, the human operator sends the robot corrective signals, for example in the form of push-button, vocal, or EEG signals to correct its actions and guide it for successful completion of the task. Once the object is available on the destination conveyor, the human operator controls the conveyor to transfer it out of the workspace. If the robot did not perform the immediate preceding task satisfactorily, the human operator instructs it to correct. The interaction between human and robot increases human utilization factor and cognitive workload. We earlier mentioned the robot performance has a significant impact on the human cognitive workload during the collaboration between the human operator and a robot. Robot performance is measured in terms of its capability to accommodate a human operator's instructions. The robot performance, RP, for a given time instant t depends on its success in the completion of tasks, which can be modeled as given in equation 1, where RP max is the maximum value of the robot performance, PMR is the robot's mistake probability, SR is the source rate or the feeding rate of source conveyor, and DR is the delivery rate or percentage of items being handled by the robot and put on the destination conveyor at the preceding time instant. Another factor that impacts human cognitive performance is the human physical workload, which in turn related to human physical performance. A human's physical performance can be related to the muscular contraction and expansion system and can be tied to the fatigue level of the muscles and their recovery, that can be modeled as given in equation 2, where PP is the human physical performance at time instant t and FTH stands for the threshold force, which is calculated at the equilibrium point where the fatigue and the recovery balance out each other. Fmax ISO stands for the maximum value of isometric force. MVC stands for the maximum value of isometric force that one can produce at rest or the initial state or zero level of fatigue. Clearly, the maximum value of isometric force decreases over time due to muscle fatigue, that is represented in equation 3, where CF and CR stand for the fatigue and recovery constants, respectively, and F denotes the real-time applied force that reduces over time due to the increase in fatigue levels. In this model, fatigue and recovery processes are used to describe the dynamic evolution of the maximum isometric force. A major contributing factor to human cognitive performance is his or her cognitive workload. The cognitive workload refers to the amount of mental work to be performed in a given period. A human operator's cognitive performance degrades for high cognitive workloads and or while handling complex tasks. During the inactive mode or when no cognitive work is performed, the human operator's cognitive performance level gradually increases up to the optimum level of arousal point. Here, we model the human operator's cognitive workload for a given time as a function of the complexity of the tasks to be performed and the human operator's utilization factor. The human cognitive workload is given by equation 4, where the minimum and maximum cognitive workloads may vary from person to person, depending on the individual's capabilities to handle tasks. C is the complexity of the task varying between 0 to 1, and U is the human operator's utilization factor, which is a function of the robot's mistake probability given by equation 5 and equation 6. Here tau is a positive integer number representing the time constant. If the human operator is doing the same task all the time, then the task complexity will be a constant number, otherwise, its value changes depending on the task being handled. In the proposed human-robot collaboration framework, individual tasks are assumed to be independent events. Further, a task either can be failed by the robot, which requires the human operator's intervention, or it will be successfully handled by the robot, which does not need the human operator to be utilized. As earlier mentioned, human cognitive performance is a function of human cognitive workload, human physical workload, and the additional workload due to the mistakes of the robot. Incorporating all these factors, human cognitive performance, CP, can be modeled as equation 7, where CP, max is the maximum cognitive performance, CW is the human cognitive workload, HW is the human physical workload, HR is the additional workload added due to mistakes of the robot, and alpha, beta, and gamma are positive real numbers with alpha plus beta plus gamma equals 1. We would like to highlight the fact that with this model, the human's cognitive performance is at a maximum when it is subjected to a minimum workload, no fatigue, and maximum robot performance. To validate the proposed human cognitive performance model, we consider a manufacturing workspace in which a human operator and a robot can collaboratively work to transfer the produced items as symbolically shown in this slide. The source conveyor carries the incoming boxes to the workspace, and the destination conveyor moves the inspected items to the packaging area. The robot's task is to physically move the objects from source conveyor to destination conveyor based on the human's instructions. The human operator supervises and instructs the robot to complete its task correctly. The human operator is assumed to help the robot by physically changing the object orientation appropriately so the robot can pick the object easily. Also, the human operator is involved in minimal physical activity, such as adjusting the orientation of the objects on the conveyor, regulating the speed of the destination conveyor, maintaining the logs, etc. Collaboratively, both the human operator and the robot work together to transfer the objects from the source area to the destination area. To simulate this scenario, we use the derived set of equations, which were discussed in the previous slides. For these equations, to run the simulation, the parameters are chosen as summarized in Table 1. Since in human cognitive performance, the human cognitive workload is a dominant factor, the value of alpha is selected larger than the values for beta and gamma. The simulation runs over an operating period of 10 hours with the sample time of 30 minutes. The minimum level of human cognitive performance at any given instant is assumed to be more than 0.2, below which the human operator is considered to be incapable of performing the cognitive workload. In order to maintain simplicity, the robot's mistake probability has been assumed to be constant over time. The figure in this slide shows the simulation results for a fixed value of task complexity equals 0.1 and the robot performance equals 0.7. The graph shows that over time, cognitive workload increases, the human utilization increases, and human physical performance decreases. These changes result in decreasing human cognitive performance over time. The figure in this slide shows the simulation results for a fixed value of task complexity equals 0.1 and the decrease in robot performance equals from 0.7 to 0.1. We assume the task is similar at all time instants, and therefore the decay rate of physical performance is assumed to be the same. Again, these results show that over time, cognitive workload increases, the human utilization increases, and human physical performance decreases. These changes result in decreasing human cognitive performance over time. Further, it can be seen that for lower robot performance, the cognitive workload increases faster, human utilization increases faster, and hence, human cognitive performance decays faster. The figure in this slide shows the simulation results for a fixed robot performance equals 0.7 and the increase in task complexity equals from 0.1 to 0.7. Similar to the previous simulation, we assume the task is similar at all time instants, and therefore the decay rate of physical performance is assumed to be the same. Again, similar to the previous simulations, it can be seen that over time, cognitive workload increases, the human utilization increases, and human physical performance decreases. These changes result in decreasing human cognitive performance over time. Further, the results show that for higher task complexity, the cognitive workload increases faster, human utilization increases faster, and hence, human cognitive performance decays faster. The overall simulations are shown here for 3 different task complexity values, each simulated for 3 different values of robot performance. Analyzing the results, it can be seen that for a fixed value of task complexity, the human cognitive performance decreases, while its utilization factor increases for decreasing values of robot performance. The impact of task complexity on the performance values can be analyzed by comparing the results. For a fixed value of robot performance, the values for human cognitive performance decrease, while the utilization factor increases for increasing values of task complexity. Furthermore, it can be observed that in the subplots F, H, and I, the maximum operating time is less than 9 hours. This is because the human operator's cognitive capabilities have already exhausted and are below 0.2. To conclude this presentation, we would like to highlight the following remarks. In this paper, a dynamical human cognitive performance model has been proposed for a human-robot collaboration framework with the associated modeling of human physical workload, robot added workload, and human cognitive workload and task complexity. This model has been simulated for a shared task between a human operator and a robot. Simulation results validated the proposed collaboration model and analyzed the effects of variations of the involved parameters. The developed model and simulation results confirmed that the increase in cognitive workload decreases the cognitive performance, the decrease in physical performance results in decreasing the cognitive performance, the increase in task complexity causes a decrease in the cognitive performance, and finally, the improvement of the robot performance improves the cognitive performance for the human operator. In the future, we shall extend the model to establish human-robot collaboration involving multiple robots and the multiple human operators with the consideration of complex task planning and resource management. The authors would like to thank the technical support from the researchers at the Access Lab and TechLab. The authors would like to also acknowledge the support from the Air Force Research Laboratory, and Office of Secretary of Defense, and the National Science Foundation. The idea of quantifying human cognitive performance is still under development, and any suggestions are welcomed. For any questions regarding this work, please feel free to send it to the authors via email addresses. Thank you.